Hey, welcome back to Introduction to Computer Networks at NTU. This is Polly again, and we are in week 14, and this is episode 25. So for this week, we have PA9 due. By the way, I've checked PA9 already. Several of the teams have already completed PA9. Good for you. And from how I see from PA8, PA9 should not be challenging for all of you. Okay, and good for you guys. And compared to last week, we have only 4 quizzes due this week. All right. But guys, it's not quite time to relax yet, even though we have fewer quizzes. But the 4 quizzes this week are all non-trivial. Some of them can be a little bit tedious and counterintuitive. So you want to be patient walking through the quizzes with Polly. And they're all due, again, Saturday, 6 p.m. And a gentle heads up, exam 3 is coming up in 2 weeks. If you click into the exam 3 channel, you will see the exact date and time. You will also see the scope. And by the way, so Polly is not quite sure about the scope, particularly for chapter 6. So there might be adjustments to the chapter 6 part next week after the lecture. We'll see how the lecture progresses. And the exam process, I guess you guys know about it well now. If you are a little bit concerned or anxious, just check the exam 1 channel or exam 2 channel to recall the whole process. Given how you guys have done for exam 1 and 2, I don't think that you guys will have trouble for exam 3. And maybe a little bit of tip for exam 3 is this. I don't know how you feel the content that we've gone through in the exam 3 part. It's a lot more technical, you see, right? Routing algorithms and earlier part, longest prefix matching. There's more arithmetic or logic type of problems for sure in exam 3. All right. And the links for the Google form and Google Meet that you guys need to join will be available an hour before the exam. So they are not quite yet ready. All right. Good. And time to go on to talk about the topics today. Distance vector is something that we started talking about from last week, right? If you recall, quiz 41 to 44, yeah, that is to give you a sense how distance vector router works. So essentially, a distance vector router, such as router X in quiz 41 to 43, can only make decisions based on information provided by the neighbors, because router X just doesn't know where the destination is. So from local information collected, and the decision might get better and better over time as more neighbors provide better information. So this is in the local information category of routing. If you recall last week, we talked about this other routing protocol called link state routing. That one make decision based on what? The network topology, that's global information. All right, so link state routing, global flavor, distance vector, local flavor. And this week, we'll talk more about how a router makes local information and achieve optimal routes. Okay, so distance vector routing. Now we're going to talk about it more formally. The first video is to recall distance vector. If you recall the distance vector spirit video, I'm going to play it again, 1 minute, 10 seconds, just to recall distance vector. That should give you a rough sense how a router discovers a route without seeing the entire network topology. Yeah, that is asking the neighbors to help. So neighbors will be reporting how they know about the destination. Now you know the neighbor's cost to the destination, and you know the cost for you to reach each of your neighbor. So that be X, and the cost from the neighbor to destination Y. You can calculate the sum of X and Y. If the value here is not infinity, you've discovered a route to the destination.
But in order to discover the route that is the best to the destination, then you will need to check through all neighbors. Okay, for each neighbor, you find the cost to each of these neighbors. And you find out from that particular neighbor the cost to the destination. And you sum up, okay, x and y for that particular neighbor. So you pick I such that xi plus yi is the lowest. There, you discover the best route, the shortest path. And I there is the next hub that leads to the shortest path to the destination.
All right, so you pick the neighbor that tells you the best information. All right. So by the way, when Polly says best routing distance vector is always the best route at that moment in time, given the very limited information. All right. Good. Next is Polly is gonna show 2 more videos and introduce distance vector algorithm formally. In the first video, you'll see Polly introducing a notion, small d. Okay, so that stands for distance. That's to denote the distance from one node to another, from x to y, dxy. All right? And Polly is going to show you the Bellman-4 equation formally. So Bellman-4 equation is essentially doing what the distance vector spirit video is showing for all the neighbors. Find out which one gives you the shortest path to the destination. And the last part of this video is an example to exercise the Bellman-4 equation. So this video together is 3 minutes, 10 seconds.
And you see right on the slide that what I was describing is exactly how distance vector algorithm works. So we define the term here. dxy is the cost, okay, of the shortest path to go from x to y. And so what we're calculating here is the minimum cost to go from x to y, or to discover the shortest path from x to y. The way to do it is to go over all the v's. Okay, v's are the neighbors of the source. For each v, we calculate the cost to go from the source to the neighbor, plus the cost from the neighbor to the destination. So the sum here is the cost to go from the source to the destination through a particular neighbor v. So all we need to do is just to go over all the neighbors and calculate the sum for each neighbor and pick the neighbor that gives us the minimum value. And that minimum value is the minimum cost, okay, from x to y. And that v there is the next hop along the shortest path to the destination. So by doing this calculation here, we discover the shortest path. We discover the minimum cost. And this equation here is better known as the Bellman-4 equation, because this algorithm implemented in distance vector routing is devised by these 2 great guys. Let's try to exercise the Bellman-4 equation using an example. And let's calculate the shortest path from U to Z. Right? The first thing to do is, hey, we need to have the neighbors, right, reporting, okay, how they know about the destination. So use neighbor including V, W, and X. So V will need to report the distance from V to Z, and that is the entry here. X will have to report the shortest distance from X to Z. Same for W to report the shortest distance from W to Z. And then we can begin, okay, doing the calculation. So we'll be going through all 3 neighbors one by one. So let's take the first neighbor V. Okay, so link cost from the source to V is 2. And dVz is 5. So we have 2 plus 5 here. Okay. From U to Z through V, the cost is 7. Second neighbor, X. So this is the second one. Link cost, okay, from the source to X, 1. And dxz reported as 3. So this is 4 here. Wow, nice. Third neighbor, W. Link cost is 5. And dwz, 3. So together, 8. So obviously, 4 is the minimum value. This is the minimum cost from U to Z. And you know what? X is the neighbor that gives you the minimum cost. Therefore, X is the next hop leading to the shortest path. So here, X here, achieving the minimum, is the next hop in the shortest path. And that is also, okay, the link pointing to X is the link interface to insert in the forwarding table for destination Z.
All right, so Bellman-4 equation. Next is to formally introduce the algorithm. You'll see Polly introducing yet another notion called big D. Okay, so this big D is the distance vector of the router. So what that means is that it's a collection of all the small d's, the distance from this router to the potential destinations. So a bunch of them composing a vector. And in the video, you will also see how Bellman-4 equation is finally applied in the distance vector algorithm. And it's essentially an endless loop of 3 steps. First, collect the distance vector from the neighbors. Second, apply the Bellman-4 equation and derive the new distance vector for this router. And if there's better routes discovered, better paths discovered, this router then will further propagate the new distance vector to the neighbors so that the neighbors can continue to derive better routes. So this video, a little bit longer, 5 minutes, 40 seconds.
So that was the Bellman-4 equation, which captures nicely how one discovered the shortest path, the minimum cost to go from the source to the destination. But you see also in the previous example, right? Calculation of the Bellman-4 is actually based on these information, Cij, okay, the link cost from the source to each of the neighbors, and these, the shortest distance from each of the neighbors to the final destination. All right. That is also saying the distance vector algorithm as a whole contains the Bellman-4 algorithm, but before the Bellman-4 can be calculated, each node will also need to collect these information. Now, this is actually configured in from the network admin when the network is established. Now, this actually relies on the neighbors, okay, sending their routing information to the node. Okay, so next, what I'll be talking about is to go over the entire distance vector routing algorithm, covering both the message passing part as well as the Bellman-4 part. Now, before I talk about the entire distance vector routing algorithm, let me introduce just one more notation. dxy is the shortest distance from x to y. This is not new. The new one is here. A node is going to maintain the shortest distance from itself to every possible destination existing in the network. So capital N here is the set of the nodes in the network. So we do have multiple values of these dxy, okay, because there are multiple values of these y's. So each of these values is the distance, the shortest distance to a destination in the network. Therefore, we call this a distance vector. It's denoted as capital D. Okay? Now, because this is the distance vector for node x, therefore it's called the dx. Good. So the distance vector routing algorithm, the goal is to derive dx, okay, for each node x. Right? And before we could calculate dx, okay, the node here needs to have 2 pieces of information. Okay, according to the Bellman-4 equation, we need to know the link cost from the node to each of the neighbors, so Cx fees. Now, in order to have the shortest distance from each of the neighbors to a particular destination, yes, we need to also know, okay, the neighbors' distance vectors. So for each v, node x here also maintain dv. And now the algorithm of distance vector routing. You see here, okay, key idea is it works in 2 phases. First of all, each node sends its own distance vector to the neighbors. So this is the message passing phase. And then 2. When the node receives the distance vectors from all the neighbors, Bellman-4 equation calculation begins. And as a result, okay, the node x there discovers its own distance vector. And we could loop back. Okay, this node here then will pass the dx to the neighbors. Okay, that is the general idea of distance vector routing algorithm. Okay. The Bellman-4 equation, now this is the Bellman-4 equation. Okay. Know that when x receives all these dv's from the neighbors, okay, dx is not just one value to one particular destination. So this Bellman-4 equation is going to be called, again, these many times, so that we derive the shortest distance to each of the possible destinations in the network, n. All right. Final note here. Under minor natural condition, the shortest distance from x to y, at the beginning, it might be really, really bad, okay? But as time goes by, it's going to converge to the actual least cost. So minor natural conditions means that, for normal internet operation, this is going to hold true. To be more precise, this is distance vector routing algorithm, and it's depicted such that it looks like it's working in cycles. So each router in the network operates such a cycle. First, it's going to wait for one of these two events. Very common is that you receive a distance vector from the neighbor. Occasionally, this router here might detect there's a link cost change among these links to the neighboring routers, because these two events might affect the result of the Bellman-4 calculation. So when these two events occur, we trigger Bellman-4 calculation to begin. As a result, we get a new distance vector. Now, if the distance to any of the destination has changed, that means, better route discovered, shorter distance discovered. Then we tell to the neighbors, because the neighbors might also benefit from the good news, benefit from the discovery. Right? So you see, distance vector routing algorithm working this way, it's iterative, meaning it works in cycle. In each cycle, it can only be triggered by two kinds of events, link cost change and DV update messages arriving at the router. It's also distributed because one can calculate and discover a better route and pass it to another node. So each node notifies the neighbors of a better route, and the neighbors then calculates even better route and notifies the neighbors. So in the end, they converge to the shortest path, but the effort is actually shared, distributed, and contributed by all the routers in the network.
All right, so that's distance vector routing. Yeah, so you hear Polly mention converging to the best route in the video. So that convergence time is usually related to the diameter of the network. Yeah, because every round, information gets propagated further. So it takes usually the diameter rounds to propagate the information throughout the topology. All right. Now that's exercise. All right. And that's exercise through an example. So in the next video, 5.5 minutes, you'll see Polly initializing the distance vectors, for each router in the network. And you will see also that Polly tries to calculate, update the distance vector for one of the nodes in the network at the next cycle. That will be T0 for initialization, T1 for the first cycle. And right after that, you will be working on quiz 45, developing the distance vector for another node at T1. All right, ready?
Okay, example time. In order to make sure that you understand this thing clearly, let's use a concrete example. So the example this time, very simple, only 3 nodes, x, y, z, and they are fully connected. Oh, by the way, we have not yet talked about initialization of the distance vectors. In node x, the distance vector of x is initialized this way. For destination x, well, it's itself, therefore, distance 0, it does not cost anything to transfer data from x to x. To go from x to y, let's initialize it to the link cost of xy if they are adjacent to each other. So 2 here. xz, so xz, they're adjacent, therefore we use the link cost between xz. Similarly, you do the same thing to initialize dy for node y, dz for node z. Now, in node x, it maintains all neighbors' distance vector, alright, but at the initialization phase, node x did not receive anything from y nor from z yet, so dy and dz, these two vectors, are left null. So I'm just using the sign of infinity there to represent their null. Similarly, for dx and dz in node y, and so on and so forth. So this is how you initialize the initial distance vector table, which is composed of 3 vectors. You maintain your own vector, you maintain also the neighbor's vector. Now, once the vectors are initialized, each router will what? Okay, notify the neighbors. So this vector here will be sent from x to all the neighbors, y and z. Similarly, node y is going to send its initial table to x and z. And similarly, z sent to y and x. All right. And that's why, okay, in the next cycle, node x here in the table is going to see dy from node y, dz here from node z. All right. Now, with neighbors distance vector in place, now we can begin to calculate dx. So what is the value of dxy? What is the value of dxz? Now let's start from calculating dxy. Right? So the Bellman-Ford equation says we try through all the neighbors, okay, of the source. X is right here, the source. Two neighbors, y and z. So yeah, we do have two entries here. Okay, one is assuming neighbor being y. Second, using neighbor z. So, okay, for the first sum, we use the link cost from the source to first neighbor, and then adding the shortest distance from the neighbor to the destination. Now, in this case, neighbor happens to be the destination, so this is 0, okay, as dy y says 0. Link cost xy, 2, so 2 here. Now, for the second neighbor, z, link cost of xz, 7, so 7 right here. Shortest distance from neighbor z to destination y. Okay, then we need to look up the table. From z to y, right here, it says 1. So 7 plus 1, this is 8, and this is 2 only. Therefore, y here wins. Okay, y is the next hub router, okay, to y. So therefore, we write 2 right here, okay, for x, y. And now we derive dxz, okay, so from x to z. Again, from the same source, 2 possible neighbors. One is y, the other is z. Link cost from x to y, 2. So 2 right here. Shortest distance from y to z, we'll have to look up the y row here to z. So the distance vector from the neighbor y suggests it should be 1. That's what we are seeing here. Now for the second neighbor z, link cost from x to z, 7. So 7 here. The shortest distance from neighbor z to z, trivial. And yeah, it should be 0 here in the table. So this is 7 and this is 3. Therefore, y wins again. To go from x to z, take this path. And we can add 3 back to the distance vector of x. And what do we do next? Yeah, now x here acquired the new distance vector. It's going to what? Send it to all the neighbors. Okay. So this is the first cycle, calculating the dx, okay, from the x's point of view. Similarly, node y there is going to be calculating the dy. Node z there is going to be calculating the dz because it's receiving dx and dy.
All right, time for quiz 45. All right, so this is the exact topology you see in the video. All right. Oh, wait, I need to go to the, whiteboard mode. So this is the exact topology you see in the video. And in the video, Polly has derived the table, okay, for node x at T1. So I ask you to develop the table for node z at T1. And that is essentially this. Yeah, Polly just calculated this table. Now you do this one. That's essentially calculating the small dzx and the small dzy. All right, let's go to the Discord space, channel W14, quiz 45. And guys, this is the first time you exercise distance vector routing algorithm. So let me give you 10 minutes time, all right? And be careful. It's a little bit counterintuitive. You might want to follow the algorithm strictly instead of try to find out some sort of intuition to do the computation. All right, so let's start counting time. 10 minutes. Oh, by the way, guys, show the derivation. All right. nice. Very good. Very good. I guess it's intuitive for the class this semester. Congrats. Okay, very well done. And we don't need 10 minutes. In fact, it just took us 10 minutes. Very good. More time for the lecture. Now, in case some of your teammates are still wondering, you know what? No worries. Let's come back to the video. In the next video, Polly is going to derive Z's table at T1 as well as Y's table at T1. So we have T1 completely derived. Let's try to calculate the distance vector of Z together. So you see, it will be the shortest distance from Z to every possible destination in the network. And in the network, it's very small. Starting from Z, there are only two possible destinations, X and Y. So we just need to calculate dzx and dzy. Now let's calculate dzx first. According to Bellman-Ford equation, okay, so what we do is to try to find out, okay, through all these neighbors connected to the source, okay, which one leads us to the shortest path to the destination X. Now, in this network, we do have two neighbors, okay, connected to Z. So let's try the first neighbor first, which is Z. So we'll be using the link cost from the source to the neighbor. So link cost from source to neighbor, Z to X being 7. And then based on what the neighbor knows, okay, the shortest distance to the destination. In this case, neighbor is X, destination is also X. Now we look up the table. So dx here being known to Z, according to that, the xx is 0. Now the second entry, the second neighbor is y. Okay, so we'll then take link cost from Z to Y, which is 1, and then based on Y knows the best to the destination X. So dyx, okay, is the value we need to add link cost zy to. And according to the table, okay, dy says dyx being 2, therefore 1 plus 2. So going through X, we get a pass. The cost is 7. Going through Y, we get a pass that the cost is only 3. Therefore, 3 wings. Okay, so you see here, to go from Z to X, the shortest path distance is 3. And the next hop is obviously Y. Well, let's calculate the other entry, which is zy. Let me clear the markup first. All right. Okay. Again, according to the Bellman-Ford equation, source is Z, and the destination we wish to find out the shortest path cost is Y. Yeah. In the Bellman-Ford, we'll try, right, for 2 different neighbors in this network of Z and C, which lead us to the shortest path. So let's try the first neighbor here, X, link cost being 7 again, and then, what about dxy? Now let's look up the table. It's dxy, therefore, yeah, the shortest distance is 2. So we ended up adding 7 to 2, which is 9. That doesn't look so good. What about the other neighbor of Z? zy is 1 again. What about the shortest distance from Y to Y? And hey, it's itself. So Y to Y, the cost is 0. So okay, this other path going through Y give us only path cost 1. Therefore, yeah, going through Y, this gives us the shortest path from Z to Y. And therefore, we update the entire dV, which is now 310. We can actually continue and calculate what is dy, isn't it? So there are again 2 entries, yx and yz. Let's calculate yx first. Okay, this time y is the source and destination is x. Again, we need to try through all the neighbors of y. So let's start from x. Okay, so x in the middle, source being y, destination being x. So we go through link yx, which is 2 here, and then find out what is the shortest distance from neighbor x to the destination x. So neighbor and destination happen to be the same node. According to the table, xx, yeah, the value is 0. So here, going through neighbor x, ooh, nice, total cost is 2. The other neighbor, so y's other neighbor is what? Z. So z in the middle here. Link cost yz, 1. What about the shortest distance Z knows to the destination X?
So dzx, we'll have to look up the table here. dzx, which says 7. So the best path, okay, going through neighbor z is unfortunately, costing us 8. So comparing the two, the path going through neighbor x is better. Okay, so y, x, and then reaching x. So total cost 2. So we can now update, dyx to 2. The second entry in the distance vector of y is dyz. Okay, so again, starting from y, going to the final destination z. So starting from y, and this time final destination z. We'll have to try through both neighbors. First neighbor being x, link cost from y to neighbor x is 2. The shortest distance from x to the final destination z, dxz. So let's see, dxz. The entry in the table says 7. Second neighbor being z here, so yz, the link cost is 1. Nice. What about the shortest path from z to the final destination z? It's actually quite straightforward, isn't it? zz, trivially 0. And 9 comparing to 1, which one is shorter? 1 here. At this point, we can also update the entry dyz. And this is how we come to the distance vector of y. So we now finish deriving all the distance vector tables at time t1. What you see also is this. Look at this. dy and dy. Okay, between t0 and t1, dy did not change. Therefore, dy here, no y here, does not need to propagate the data. Okay, propagate the vector to no x and no z. While, okay, when x here finds out the dx, which is different, okay, from t0's dx, we'll need to propagate dx to no y as well as no z to calculate the table for t2. Similarly here, z find out the new dz being different from the old dz, we'll need to propagate also. Okay, dz to no x and no y. Therefore, the two other nodes can calculate if the dx and dy needs to be changed further.
All right, so that's full T1. What about we continue to develop the distance tables for T2? Oh, by the way, as Polly introduced this matrix there, 3 to 3, I call it the distance table. It's in fact just the table for the derivation purpose. In Bellman-4 equation, in distance vector routing, there's no such term, distance vector table, all right? It's just for the derivation. So let's now check out for T2, how the derivation will continue.
So after the quiz, you'll see dx is changed and dz changed as well. So no x and no z will be propagating, okay, the newly discovered, the better distance vector, like this. Okay. So no x receiving the update is going to replace this with a new distance vector. Right. Just like y here, okay, this vector here is going to be also replaced with a new vector from z. Similarly, this vector here is going to reach z, and z is going to update from 0 to 7 to 0 to 3. Now, what's a bit special is this. Okay, in the quiz, you see that dy here at no y is actually not changed. Therefore, no y here is not going to distribute to 0, 1, okay, to x nor to z. Okay, so this stays the same. Therefore, this and this stays the same. But no y here is going to receive a new dx and new dz. Therefore, this gets changed to 0, 2, 3. This gets changed to 3, 1, 0. You see that in cycle number 2, x, y, and z, they actually converge. Okay, the view is consistent, and they all converge to the shortest path, okay, the least cost path. So in this very simple example, we see distance vector using the Bellman-4 equation works really well. Converges in 2 cycles.
All right, so that was distance vector routing. And if I may, Let's come back to the Discord space, channel W14 quiz 45. So we here have a solution that's using the algorithm books notation, but works equivalently well. All right, so I get, so Sherman, Team 13 gets a geek mark here. All right, and we move on. So distance vector. It's a lot more scalable than link state routing. If you recall, the reason that we talk about distance vector routing is because in link state routing, we do n-square computation, big O n-square computation time. We have also potentially n-square, a big O n-square scale message propagation, and potentially also big O n-square memory requirement to store the network topology in each router. So there's actually also an issue with distance vector, because distance vector doesn't have those scalability issues. But distance vector does have this issue. Bad news travels slow. So until now, in that example we just showed, and in quiz 45 you guys try exercising. That's a network that's stable. There's no link cost change. When we are in a network with link cost change, or some nodes might pop up or go down, when there are changes, distance vector might not be that pleasant. Okay, so it does have this property when the link cost, for example, is reduced, or a new link is added between two nodes that are previously not linked. Those good news will travel really fast. So when that happens, you see that if you recall in distance vector, there are two situations that would trigger a router to reapply the Bellman-4 equation. One is link cost change. The other is receiving distance vector from the neighbors. Yeah, so link cost change, including becoming better or becoming worse, will also trigger the Bellman-4 equation, and the result will also be propagated. Okay, so when the news is good, link cost reduced, link being added, it will travel fast. But on the other hand, when link cost grows or a link suddenly brought down, bad news will travel slow, and it can be very, very slow. In some extreme case, it could count the link cost to infinity, meaning it does not converge. All right. So today we only have time to cover the good news travel fast case. So let's check out a link cost case and how we quickly converge to the new cost.
So one very interesting property with the distance vector routing is this. Whenever there's a good news in the network, it travels really fast. Okay, so when there's a better route, it gets propagated really fast and everyone converges really fast. But if it's bad news, meaning if a route suddenly goes bad, okay, it will take a long time for everyone to discover, okay, the route is really bad and we should really be going another way. So let me describe the first case, the good news travel fast case. So recall, okay, this is the change where the link between x and y is reduced from 4 to 1, so good news. The node is going to detect local link cost change and update the routing information and trigger Bellman-4. If the distance vector changes, then send to the neighbors. So here, link change from 4 to 1. So at time 0, y is going to detect the link cost change and update its DV and inform the neighbors here and here. So next point in time, z here, is going to receive this distance vector from y. Okay, it's going to see, oh, the shortest distance from y to x is now 1. Okay, therefore, z is going to update the shortest distance to what? 1 plus, the cost from going from y to x, which is 1 now. That is 2, which is better. Okay, so z is going to update its own dB and send it out to the neighbors. And y is going to receive z's update. Z says, okay, the shortest distance to x from me is 2. And y sees that, hey, I do have a direct connection. My shortest distance is already 1, right? Your shortest distance to x is 2, plus the link cost from y to z. This path is not better. Okay, so y there will not discover a new path, okay, a better path to x. Therefore, distance vectors stay the same, okay, no more message being sent out, okay, back to z. Network converges. Everyone goes to the steady state. The second case is the bad news travels slow. So you see from the scenario, the link cost instead of dropping to 1 now goes up to 60. Super bad news. Of course, x and y here would detect there is a link cost change. But in this scenario, it would take us 44 cycles until the network goes back to the steady state, until they all converge to valid shortest path. Okay. Now, bad news travels slow, meaning routes converging slowly. Okay, that is also referred to as the count to infinity problem. Now let's go to a quiz to see what's going on there. Okay.
All right. Yeah, we don't have the time to go through the quizzes to demonstrate bad news travel slow. We're going to do that tomorrow. All right, and we're gonna do that tomorrow early in the morning. So, guys, you might want to come. Make sure that you come to the lecture tomorrow, because bad news travel slow is definitely not intuitive. And by the way, Sherman, Team 13. Let's see. Working on a bad news travel slow case, whether the notation from the algorithm book will suffice. Okay. It might be a little bit tricky, all right, and you might need to end up using the Bellman-Ford equation we use in the textbook. All right, good. And you know what, guys? We'll end the lecture today early. That's great. It's 2:06, and tomorrow, make sure that you come at 2:20. All right, bye. Here's the cue.